So students, in this video, let us discuss what is called forced oscillations. Now this forced oscillation is also a kind of simple harmonic motion, but forced oscillation makes some difference with that of the damped oscillations what we have discussed earlier. Now, as the name suggests, forced oscillation. Now, these oscillations are under the influence of external periodic force, external applied force. That is, you are applying force and making the oscillations happen. If I don't apply force, suppose if I don't apply force, then the oscillations will die after some time and they become damped oscillation. So in this case, here we are applying a constant force and making the oscillations happen. Hence, the oscillations also follow depend upon what is the force applied. So I can say forced oscillations are under the influence of these kinds of forces. So what is the first one? The first one is the forced oscillations are under the influence of these three kinds of forces. The first one is resistive force or the damping force, which is existing in the environment. Because any oscillations are happening, there is a force acting on it which is trying to halt the oscillation. And the second one is there is a restoring force acting on the body, and hence SHM, simple harmonic motions, are happening. And the third one is the applied force. Now, this restoring force exists by nature in any case of simple harmonic motion. And suppose if I don't apply any external force, the oscillations die naturally because there are damping forces which are acting on the oscillations and trying to bring them to the halt. Now, in this case or special case of forced oscillation, we are also applying external force. So if I say let the restoring force be given by minus k into x, the damping force is given by minus r into dx by dt, where r is called damping coefficient and dx by dt is called velocity, where r is called damping coefficient. And let me say we are applying an external periodic force. Let our applied force be periodic in nature and let the force be defined by F into sine Pt, where F is of course the applied force and P is the frequency of the applied force, the frequency. So let me say P is the applied frequency. So because I'm saying let the applied force be periodic, I have taken a sine function of the periodic. So what is the equation of motion? So I can say the total resultant force acting in the case of periodic oscillation are due to these three forces. So hence I can write this as sum of damping forces, restoring force, and external periodic force. Also, you can understand here looking into the equation, the damping force I have included minus here, indicating that this damping force tries to bring the oscillations to halt. So the direction of applying of force is opposite to that of the motion of the body. If you want something to bring it to halt, you have to apply a force in the opposite direction. and hence a minus sign. Restoring force is also negative because this is also trying to bring the material to halt to its equilibrium position. Hence, the direction of restoring force is negative. And the applied force, because this is a driving force, I have taken this as positive. So if I write resultant force as m into d square x by dt square from Newton's second law of motion, mass into acceleration. So I can rewrite this equation as r into dx by dt plus kx is equal to f sine dt. Now this is the equation of motion for a forced oscillation under the influence of three kinds of forces. So one is external applied force, restoring force, and damping force. Now, what are the examples for this forced oscillations? As the name suggests, oscillations under the influence of external force. So, what good example we can give? The first one, suppose you push a swing with some applied force, you make the swing oscillate. So the swing keeps oscillating as long you are pushing the swing. The swing could be vacant or occupied, nevertheless, but even then, the oscillations of the swing depends on what is the force you are applying. So if you push the swing with more force, the amplitude of the oscillations of the swing is definitely proportional to the applied force. I can give the second example is say vibrations produced in eardrum. We know that sound waves are pressure waves. So whenever these pressure waves are falling into the eardrum is a thin membrane, a diaphragm. There is a diaphragm inside ear. Diaphragm is a thin membrane. And this diaphragm keeps vibrating depending on the applied frequency. Higher the frequency, higher the pitch of the voice, that much is the higher the vibrations. So I can say the diaphragm's vibration depends on the external voice or the sound or whatever. So as long as there is sound, the vibration, the intensity of vibration also depends on the applied sound. So we can give many more examples like this. So where the oscillations do exist as long as the driving force or the cause is existing. Once you remove the applied force, the oscillations become damped oscillations and they die naturally after some amount of time. Thank you.